When you first start your NDT journey, most of your theory training happens up front. But by the time you log all your on-the-job training hours and you're finally eligible to take the exam, that classroom knowledge isn't always fresh anymore. That's where the Liquid Penetrant Test Prep app comes in. With this app, you can keep your theory sharp while you build hands-on experience. It features two learning modes. Study mode gives you instant feedback and clear explanations for every question, helping you understand why each answer is correct. Test mode recreates the pressure of the real exam so you can strengthen your focus, speed, and confidence. Study anywhere, on breaks, in the field, or at home. The app tracks your performance automatically, showing you exactly where to focus next, so every minute of study moves you forward. Download the Liquid Penetrant Test Prep app today on the Apple App Store and take the next step toward a safer, stronger career in non-destructive testing.
Welcome to the Deep Dive. We unpack dense technical sources to give you the core insights. Today, we're looking into comparators and reference panels in liquid penetrant testing. These aren't just blocks of metal. They're carefully engineered standards designed with specific flaws to really challenge penetrant systems.
And it's a necessary challenge,
Yeah.
because the reality of manufacturing is pretty staggering. When engineers first started looking for process-induced cracks in, say, aircraft parts, what they found was shocking. Some titanium-forming cracks were as small as 7 micrometers. It was just a 0.00003 inches, incredibly small.
7 micrometers, that's already hard to wrap your head around, but you said it gets even smaller.
Oh, yeah. Some stainless steel welding defects, down to 2 micrometers, too.
Oh, wow.
Yeah. So you immediately see why just looking isn't enough and why our reference standards have to be so rigorous.
Exactly. If the flaws we're hunting are that microscopic, the tools we use to check our detection methods, well, they need to be just as demanding. So our mission today is to sort of trace the development of these comparators. We'll go from these complex fatigue simulators to more advanced panels and really understand how they help monitor effectiveness, repeatability, and that key thing, discrimination. Today's deep dive is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions helping companies build stronger, non-destructive testing programs. Making sure your testing hits these levels of precision, that needs top-tier compliance. You can learn more about them at the link in the show notes. Okay, so let's kick off with what the source calls the modern benchmark for simulating these flaws. The low cycle fatigue specimens, LCF specimens. These are the purpose-built, engineered standard, right?
That's right. That's really where high-precision work starts today. They're designed specifically to mimic those tight fatigue cracks you find in high-strength alloys, nickel, titanium, then gas turbine engine parts. The key here is controlled crack growth. It's not random. They aim for a specific aspect ratio, usually around 2:1, length to width.
And that level of control is why they're used for the really critical stuff, like the Qualified Products List, QPL AMS 2644, for classifying fluorescent liquid penetrant testing systems.
Exactly that. For the official QPL stamp, they'll process, say, 5 of these specimens. Then they measure the luminance, basically, the brightness of the indication with a photometer.
Yeah.
And that measured light output compared against a known standard, that's what determines the classification.
But, okay, here's where the source throws in a really important point, almost a warning. Luminance gets you classified, but it isn't a direct measure of sensitivity. Can you break that down?
Yeah, this is crucial. You might get the paperwork right, pass the QPL test because your system was bright enough under those lab conditions. But you could still miss flaws in production if your process control isn't tight. Luminance is just light output in a specific test. Sensitivity is the actual ability to find that tiny 2-micrometer crack out on the floor. Things like poor pre-cleaning. That can mess with luminance readings, but doesn't tell you if you can actually find the really small stuff.
It sounds incredibly precise, the manufacturing. Computer-controlled hydraulics for the loading, special methods like EDM slots or spot welds to initiate the cracks. They're really trying to pin down these tiny flaws.
They absolutely are. And the loading itself, often they use a low stress ratio, like R equals 0.1.
R equals 0.1, meaning they're just barely pulling the crack open each cycle.
Exactly. Just enough to grow it, but keeping it super tight, mimicking that real-world fatigue. That's part of what makes these specimens so, expensive and difficult to work with.
So, given the cost and the precision, are people using these LCF specimens for daily checks? Or are they mostly for that initial QPL qualification?
Mostly the latter. Initial classification, maybe requalification checks. For day-to-day use, there's a huge hurdle. Cleaning them. These are fatigue cracks, remember? Super tight, deep sometimes. Back in the day, we used ultrasonic cleaning with Pretty aggressive chlorinated solvents, stuff you wouldn't dream of using now.
Right, those are mostly gone.
Yeah. So now, trying to get cleaning agents deep into that tight crack and then get them out again, it's incredibly difficult. Reusability is a major headache.
Okay, so if the high-tech LCS are tricky to reuse, what came before? Let's talk about the older ones, the quench-cracked aluminum comparator blocks.
Ah, the historical standard. You'll still see them mentioned in codes like ASME, AMS 2644, but mostly as a reference point. The general feeling now, though, is they just don't offer the discrimination needed for modern, high-sensitivity penetrants.
And how did they even make these? You can't just order a cracked block, can you?
Well, you kind of make it yourself. You take a specific aluminum alloy, 2024 T3 usually, heat it way up like 510 Celsius, that's 950 Fahrenheit, then plunge it into cold water.
Thermal shock.
Exactly. That shock creates a network of cracks. Sometimes you have to do it a few times.
And they have that groove down the middle, right? For comparing a test penetrant against a standard side by side. But didn't the source mention a problem with that? Interference.
That's a big issue. Even with the groove, if the two penetrants you're comparing have very different surface tensions, they can actually creep across and affect each other. Messes up the comparison. So if you're doing a really critical test, maybe comparing performance at high temp versus room temp, you absolutely have to cut the panel physically into separate pieces. No chance of interaction.
So lack of uniformity between blocks, poor crack types, that's really why they're not ideal anymore.
Pretty much. They tend to have larger medium cracks, not the really tight ones we need to find. So they don't differentiate well between a great system and just an okay one. Plus, they're not uniform block to block. And cleaning. Forget about full reusability, especially if you've used a visible dye on it. Once that residue can kill the performance of a fluorescent penetrant later. The source basically says don't reuse them more than 3 times max. They put too much guesswork on the inspector.
We'd also like to recognize Skaggs Media LLC as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com. Okay, so LCFs are tough to clean, quench blocks aren't discriminating enough. What's the workhorse panel? The practical, repeatable one for checking process variables day to day? That seems to be the surface-cracked nickel-chrome panels.
Yes, these are really useful for evaluating your process because they're designed to be reproducible and, importantly, very sensitive to how you clean them. The construction is quite clever. You start with a base, maybe brass or copper, plate it with nickel, and then add a final brittle layer of chrome plating.
And you make the cracks just by bending it?
That's it. Bending the panel fractures the brittle chrome layer. You control the crack depth by how thick the chrome is, and the width by how much you bend it. So you can make panels with cracks ranging from, say, 0.5 micrometers up to maybe 10 micrometers. Gives you controlled range.
And because these are shallow cracks just in the surface plating, I bet the cleaning step is even more critical than with the deep fatigue cracks.
Absolutely critical. A tiny change in your removal process makes a huge difference. Like if you change your emulsifier dwell time from 15 seconds to 60 seconds, big difference. Or switch wash pressures, massive change in the result. But that sensitivity is exactly why they're great for checking if your process is consistent. If you run the panel today and get one result and tomorrow it looks totally different, you know something in your process steps drifted.
Okay, that leads us to another specific type. The Liquid Penetrant System Monitor Panel, the PSM panel. Pratt & Whitney developed this one, right? What's its unique job?
The PSM is really designed as a quick daily check for major system problems. Think sudden gross contamination or maybe the water temperature or pressure in your wash station went way off. It's a go-no-go indicator for big shifts. It typically has 5 crack centers made with hardness indentations to give different severity levels, plus a grit blasted area. That rough area helps you monitor the background fluorescence and how well your wash step is working.
And the source really hammers home that this panel's value depends entirely on the technician looking at it.
100%. This is where the trained eye is irreplaceable. The panel might still show the cracks, right, but maybe the indications look dimmer or fuzzier than usual. Perhaps the developer isn't pulling penetrant well or the wash left too much background. The experienced technician needs to see that and recognize, hold on, this isn't right, compared to how it looked yesterday or compared to a reference photo.
And importantly, that trained technician, if they have the right certification level, they can make the call. They can look at that panel, interpret the result based on their training, and decide if there's an issue that needs action. They don't necessarily need to run off and find an engineer immediately.
That's correct. That certification signifies they understand the standard and how to interpret deviations. It's a key part of process control.
Okay, let's shift gears a bit towards actual measurement, getting quantitative. But before the fancy panels, we need to talk about developers. They play a huge role, don't they?
Oh, massive. Especially when you're inspecting opaque parts where you can't see the penetrant inside the crack. Developers boost the indication brightness in, well, basically three ways. One, they draw the penetrant out, increasing the effective therm thickness you're looking at. Two, the white particles provide a reflective background, making the fluorescence pop. And three, there's something called dilution expansion augmentation.
Dilution expansion augmentation. Okay, simplify that for me. Does it just mean spreading the fluorescent stuff out?
Yeah, that's a good way to think about it. The penetrant gets drawn into the much larger developer particles. Instead of being packed tightly in a tiny crack, the fluorescent molecules are spread over a larger area within the developer. This larger surface area interacts more effectively with the UV light, making it fluoresce much more brightly than it would down in the crack.
And is this a small boost or?
No, it can be huge, often more than a full order of magnitude, like a 10-fold increase in apparent brightness. It's absolutely vital for seeing those really tight flaws.
So to actually measure that effect and the overall system performance quantitatively, we need something different. Enter the fractured glass step wedge panels.
Right. These are pretty neat because they let us move beyond just looking at brightness to getting actual numbers. They're made of special glass. It's transparent to the UV inspection light, but opaque to visible light. This means you can see the penetrant trapped in the cracks from underneath and measure its brightness directly. The panel usually has steps, maybe 6, with cracks going from very fine to coarser.
And the main goal here is generating these brightness contrast curves, like the H&D curves from old school photography. What do those curves tell you?
They quantify really critical things. First, the slope or steepness of the curve called gamma measures brightness contrast. Basically, how what the system distinguishes between different levels of penetrant, which relates to sensitivity. Second, you look at the curve spread. You run the test with different remover contact times and see how much the curves shift.
Ah, okay. So gamma is sensitivity, and the spread tells you how robust the process is. Like, if the wash time is a bit off, does everything fall apart?
Exactly. A wide spread between curves for different wash times means your system is really sensitive to variations, maybe unreliable. A tight grouping of curves shows a more stable, forgiving process. They also look at the half brightness point on the curve as a kind of average measure of system performance.
But even with these specialized glass panels designed for measurement, that darn wash step is still the tricky part.
It's always the challenge, isn't it? With some of these glass panels, the cracks are tapered wider at the top, narrower at the bottom. So if you overwash even slightly, you might remove only a small depth of penetrant, but that translates to a much larger volume loss because of the taper, controlling wash time, temperature, pressure. It's never just a suggestion. It's absolutely essential if you want results you can actually compare day to day.
So we've really seen the range today. From those super precise but hard to clean LCF specimens for certification to the old quench blocks that are more historical reference, then the nickel chrome panels that are great for checking your process variables, and finally the fractured glass for getting hard quantitative data. It seems without these kinds of reference standards, liquid penetrant testing would just be subjective.
Completely subjective, yeah. But I think the lingering thought, the real takeaway that connects all of these, is how incredibly difficult perfect reproducibility is. Think about it. No matter how you make a crack fatigue, quench, fracture, the very tip, the initiation point, has dimensions that are practically infinitesimal, submicrometer. And those tiny spaces have immense capillary force.
So the very thing that makes the crack hard to find its tightness also makes it incredibly good at trapping, well, anything. Contamination, old penetrant, cleaning agents.
Precisely. That almost impossible to clean nature, deep down in the tightest part of the flaw, is a huge reason why results can sometimes vary unexpectedly. It forces everyone to rely heavily on frequent checks, on rigorous calibration against these standards, however imperfect they might be. It's a constant battle with the physics at the microscale.
Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training and mentorship, or compliance solutions like NADCAP and FAA readiness. To learn more, visit amsl3.com. And don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support: NDT Level 1, $1 per month; NDT Level 2, $2 per month; and NDT Level 3, $3 per month. Or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.